Welcome to this lesson on yet another of the advanced quantitative concepts you will encounter on the GMAT sequences and patterns. So the first thing to deal with when it comes to sequences and patterns is just the basics of sequence notation. So we have a sample sequence here illustrated on the screen, and you'll see different parts of it. And you've got a big S, a little subscript n is then equal to n plus 1 over n. So what do these things mean? So we know that the big S is just the sequence title, so it's just like the term name more than anything else. So that is ultimately the least relevant part to actually calculating a sequence. The little n, though, that subscript is the term number. So this is really important. That is the number in the sequence as it's defined. And then to the right is the term value. So that's what the actual value would be for the nth term if you plugged in the values for n as were dictated by the reality for the sequence. So just let's consider the sample terms for this basic sequence. We know that the term numbers are assumed to be only integers greater than 0. So we know that the n, it can't be like a 0.5. It's got to be an actual like ordinal number of terms. So our first term is going to be n, which would be 1, and then we just have to apply the function. So n of 1 plus 1 would be 2 over n would be 1, so then that would simplify down to 2. The second term would then be 2 plus 1, which would be 3, over 2, and then you can translate that into a decimal of 1.5 if you're so inclined. And your sequence would just continue from that position on following this construct. So you'd be looking at, say, for term 3, it'd be 4/3. Term 4 would be 5/4, and so on and so forth. So that's just how a sequence works functionally. And broadly, you just have to follow the instructions as defined. So now there are specific special kinds of sequences as well, starting with an arithmetic sequence. So an arithmetic sequence has a constant difference between each term in the order in the sequence. So things such as consecutive integers, consecutive odds, or consecutive multiples are all technically arithmetic sequences because the difference between all consecutive odds, for instance, 1 to 3, there's a difference of 2. 3 to 5, there's a difference of 2. 5 to 7, there's a difference of 2. So anything that's consecutive is an implicitly arithmetically defined sequence. When you're dealing with these arithmetic sequences, because of the rules of just an unweighted sequencer set, we know that the median of any arithmetic sequence is equal to the average of the sequence as well. Again, a subtle shortcut for many of the problems that ask you to solve for something involving a sequence. And you can solve for the value of any term in an arithmetic sequence, knowing the value of the single term and the difference between them. So if I know like term 5 is 2 and the difference between all of the terms is 7, I could just count up or count down to solve anything else. So as long as you've got the value of one of the terms and the value of the differences, you can solve for any individual term within an arithmetic sequence. So this here is your technical formula for an arithmetic sequence. The value of the nth term, a sub n, is going to be equal to whatever the first term value is, plus n minus 1, so the number of terms minus the first term, times the difference as defined. So again, the technical application is available for you there if you're interested. And d, of course, is the constant difference between the terms. Now, there is a second type of sequence, and this is going to be more conceptual, not so much for solving, because a geometric sequence is just too big to really solve for on this exam fully, because it's going to take you too long. But you know that there's a constant ratio between the terms in a geometric sequence. So in a geometric sequence, you can solve for the value of any term with the value of the specific first term and your multiplier, because I don't necessarily know just with the multiplier and one of the terms what the first term was. So there is a little bit of variance here, but you could still solve for everything in a geometric sequence as well. And we know that your specific term, your a sub n, is going to be equal to the first term times the r, which is your ratio, whatever it's being multiplied by, times the, well, basically raised to the exponent of n minus 1. So whatever the number of terms is minus the first term. So you just kind of say, if we've got 2, and then we've got 10, and then we've got 50. You've got 2 times 5, then times 5 times 5, or 5 squared, and you can see how the exponent is derived there. And of course, r is the constant ratio between the terms. So these are the two technical sequences you might encounter. Now, that said, it's not really how the exam is going to test sequences in most cases to just give you a sequence like this. They're going to test your evaluation of a pattern in a more savvy and critical thinking sort of way. So GMAT quantitative patterns can just be creatively tested. And oftentimes they're related to sets and sequences, but not always. So you just have to try to recognize whatever the pattern is within the problem as it's defined. And it's going to require more recognition logically than just rote calculation. So if you find yourself, for instance, needing to use, say, the geometric sequence formula from before, that's probably not necessary because, again, you're not going to be asked to actually figure out what 3 to the 7th is. There's probably some sort of pattern that you can recognize. Now, these will also frequently seek sums, averages, or terms. So you can see some sort of combination of the pieces here. And they'll also sometimes deal with digits or repeating decimals, all those sorts of things. There's a lot of different ways that they can test a pattern. Now, the strategic implications, sometimes these are identifiable by questions that are seeking non-specific values. So if they're not asking for one specific thing, maybe a range of things, or like how many 3s are going to occur in the cycle of, or in the cycle of some sort of repeating decimal up to a certain point, or if you're being asked, what is the units digit of 3 to the 75th, you might be able to just try to find the digit repetition pattern of, say, 3. So if you're being asked for something that isn't like an actual value, but some sort of like weird thing, like what is the digit or what is the repetition term, that's how you can sometimes recognize these types of questions. They'll also often deal with ranges and approximations, not exact values. Again, you're just trying to logically reach the solution in the most efficient manner possible. Now, you're going to want to write out all your steps before you begin the calculations, because if you're just trying to solve, like, again, if I'm trying to figure out what 3 to the 75th power is, I'm not going to have enough time to do it. But if I just start writing out the repeating pattern of the 3s, 3 to the first, then 9 is 3 to the second, 3 to the third is 27, 3 to the fourth is 81, and then back to 3 to the fifth, 1 times 3 is going to go back to a 3, and it just repeats that pattern. You'll recognize it without needing to do everything. And you need to avoid auto processing your arithmetic to notice those possible patterns as well, because again, I'm really only focusing on that individual digit, as it were. So carefully evaluate the information to logically solve. And let's take a look at an example to potentially do that. So here we're going to have a question asking if the first term of the sequence is 1 and the nth term is defined as a sub n, so the nth term is equal to 1 over n minus 1 minus 1 over n, what is the sum of the first 50 terms of the sequence? Again, like, trying to do this fully is absurd under the construct of the exam and the time limitations. But we're just going to start by writing out the first term. We were told the first term is 1, that's easy. Then our second term, we're going to actually write it out. So we've got 1 over 1, because that'd be 2 minus 1, minus 1 over 2. Okay, but I'm not going to actually solve for it as 1/2. I'm just going to leave it as 1 over 1 minus 1 over 2. Then our third term is 1 over 2 minus 1 over 3. Again, just writing them out, trying to identify a pattern. Then our fourth term, I see 1 over 3 minus 1 over 4, and I might notice a canceling pattern because I'm being asked for the sum of all of these terms. And again, I shouldn't need to actually calculate and find a common denominator. That's going to be too onerous. We don't have the time to do that on the exam. But I see that my 1/2, my minus 1/2, cancels out with the positive 1/2 in the next term. My minus 1/3 cancels out with the positive 1/3 in the next term. So the sum itself is going to cancel every term in the subtraction except the one in term 50 at the very end. So everything else is getting canceled except the first term and the very beginning part of the second term. So we just got to get to the 50th term knowing that everything cancels out up to that point. So now we just write out what the term values are that we have. So our 3 non-canceled term, we have 1, which is the first term. We have another 1, which is left over from the second term. And then we just have to subtract out 1/50th. And that means we've got 50 over 50 plus 50 over 50, which would be 100 over 50, minus 1 over 50, which would be 99 over 50, or 1.98, depending on how the answer choices were presented. So that's a good example of how you have to recognize the pattern, not just fully calculate, because again, common denominator of like all of these um, denominators up to 50 is going to be ridiculous. That is not what they're asking. They're asking you to recognize the pattern and execute upon it. So how do we work through this in the future? Step one, set up the scratchpad for the problem. As always, note the sought value and the format of the choices to inform your processes. If I'm being asked for a specific value, there has to be a way to do it logically. If I'm not being asked for a specific value, I need to think outside the box to try to figure out how to get to what they're asking for in the most efficient, logical way possible. Then, step two, we need to carefully read the problem and articulate the defined sequence. We have to actually say what it is. Beware of confusing the term number for the term value. This is one of the basic mistakes that a lot of people make. Make sure that you understand how functionally the sequences are written, and write the terms fully without immediately calculating so you can recognize things like the pattern we just saw in the example. And step three, consider the best approach for solving. Take the technical path to solving if you can. That's going to be the fastest way. But you will need to consider abandoning the technical approach in favor of estimation if you can identify efficiencies through pattern recognition. And again, you might even be able to argue to me that what we saw in the previous example was really logical estimation, because we're not actually solving and summing everything, but you can also make an argument that it's technical. So that's going to be our approach for sequences and patterns. Let's go ahead and move over to the whiteboard and take a look at a couple of examples and see how we can apply these concepts in the actual exam. So we've got a sample problem solving question here involving a sequence. So just setting up the scratchpad first, we got A, B, C, D, E. We've got real numbers, so I might as well write those out here. 17, 24, 27, 34, and 41. And we're being asked, if we skip to the end of the problem, what is the sum of the second and fourth terms of the sequence? So we're looking for second plus fourth is equal to question mark. So we then have the sum of the first, third, and fifth terms of arithmetic sequence K is 51. So we know that 51 is equal to the first plus the third plus the fifth. Now, we have to think about what that means. We know that there's a constant difference. So D is what we'll just call the constant difference here. And we know that we can just articulate our first term as A. It's not, it's our A, our first term. So A is just what we'll call the first term. So then to get to the third term, we're going to have A plus 2 times the difference, because you added the difference twice to get to the third term. And our fifth term is going to be A plus 4 times the difference, because again, that's how you get to the fifth term from that formula of n minus 1 times the difference. So that means that 51 is equal to A plus 2D plus A plus 4D. Now, we're not looking for the first, third, or fifth terms. We're looking for the second and the fourth. So we know that our second term is going to be equal to A plus the difference just once, and our fourth term is going to be equal to A plus the difference 3 times. So that means that my sum that we're seeking is going to be equal to 2A plus 4D. And remember, we don't want to auto-solve for the individual variables. I'm not looking for A and D on their own at this point. I'm looking for the fastest way to get to 2A plus 4D. So now, we've got to combine like terms here. So we've got our A plus A plus A. So that means that 51 is equal to 3A. And then we've got plus 2D plus 4D, which is going to be 6D. So we see this, and we've got to get from 3A plus 6D to 2A plus 4D. So let's be savvy about it. Let's divide everything by 3 so that we get 17 is equal to a plus 2d. Then all we have to do is multiply by 2, and we discover that 34 is equal to 2a plus 4d. And that, of course, is one of our answers, choice D itself. Now, you may be thinking to yourself, why don't I just solve for everything? Well, the catch here is I actually can't solve for everything. Now, I do know that the median and average here are going to be are going to be the same. So I know that I can add up all of these things. I know that now 34 plus 51, I've got 85 is going to be equal to, well, we know 3a plus 6d, we've got 5a plus 10d, and we know we've got 5 terms, so just if we set that up, we'd have 85 divided by 5 tells me that my average, which is equal to my median, is going to be equal to that 17. But I have no idea what the difference is. The difference actually can be any number of things, because it could be that I've got 13, 15, 17, 19, 21, or it could be something a bit more disparate. It could be 9, 13, 17, 21, 25. I still get the exact same thing. So I don't want to fall into the trap of solving exactly, because I actually can't. So this is a good problem-solving example of how to work through a sequence and solve for exactly what you're looking for. Now let's scroll on down and we'll take a look at a data sufficiency example. So here we're setting up, trying to solve for the first term in sequence Q. So there's not a lot that we know, but we want to take account of it. We know that there is sequence Q, and we're looking for the first term. Equals question mark. So what we need is going to be the difference or ratio, not ratio, and at least one other term. Because again, we don't know what the mechanism by which the sequence proceeds is at this point. So condition 1 says that each term after the first term in sequence Q is 5 times greater than the term prior to it. So that means that my R for the sequence is equal to 5. But I have no idea what term 1 is, because we could have term 1 equal 5, and then everything gets multiplied through, or it could equal 6. I have no idea. Because again, you could multiply 6 or 5 by R to get to the next term, and the terms would just be different. So by itself, that's not sufficient. Our answer choices are B, C, or E, of course. Then condition 2 says that the third term of sequence Q, so term 3, is divisible by 5. So by itself, that just tells me that it's a multiple of 5. It doesn't actually say that that is our ratio. It just says that it's divisible by 5. So by itself, that also is not going to be sufficient. Now, when we combine the terms, well, we know that our ratio is 5, and we know that term 3 is divisible by 5. But that tells me nothing, because as it stands, term 3 could equal both 25 or 30. And if that's the case, then our first term could equal 5 or 6. And if we've got two different outcomes, that's not sufficient, and our answer is going to be E. And this is how you want to consider plugging in. If you're plugging in, it's got to be really targeted on a specific concept. Like here, it's the ratio. Could things change? In this case, the answer is definitively yes. The outcomes can change. And because of that, we ultimately end up with neither of the conditions being sufficient on their own. So This is definitely one of the longer tail concepts on the exam. There's a bunch of different unique and clever ways that the exam can test patterns and sequences. So go ahead into some practice problems and work your own way through some of these examples of one of the harder concepts of the quantitative section.